Welcome everyone, and welcome to Professor Lucia Bello, who is our extraordinary speaker today. She is representing the Industrial Electronics Society, and as you can see from the first slide on the screen, she's going to tell us about automotive communications, current and future trends. So Lucia will introduce herself, and so I will just say a couple of points about her career that strike me. Well, first of all, we are going to discuss, and she will going to tell us everything about time-sensitive networking, which I think is really quite an important subject today. So I'm really looking forward to that. And I'm sure that all the people attending here and all those who are going to be looking at your presentation later on, because we know that many people attending, in fact, these seminars, they will not be attending live. They will just go and look at the video later on. So she's currently a professor at the University of Catania in Italy, and we'll see a beautiful image of Catania just as a background of Lucia's video. But Lucia has been also visiting several very important universities around the world. She has been a visiting professor in Sweden, a visiting researcher in Korea, and now she has started up she's the leader of the real-time systems and network group that she founded. Well, a lot of papers, of course, important, a lot of prestigious awards, also from the IEEE. And on the top of that, also several activities and very important activities within their own societies as a women in engineering representative, and also the founder of the Women in IEES initiatives. So a lot going on. And I will not really take more time, so I will pass the floor to Lucia. So please know that the recording is ongoing, and so there will be space on the chat for questions at the end. Welcome everyone again, and Lucia, the floor is yours.
Thank you very much, Cinzia. Welcome to everybody. I want to really thank all of those who made this possible, those who gave me this opportunity. So I wanted to thank all the organizers, all the people behind this wonderful initiative of seminars for women in engineering. I thank all the women in engineering leadership, past and current, and everyone who made this possible. Also people from my society were so kind to designing me as the representative of IEES in this seminar series. So this is a short presentation of what is going on in my current activities on automotive networks. So I will introduce myself just a bit as a woman in engineering, and then I will provide you an overview on the in-car network technologies in terms of what is the current status, what are the new requirements, what are the new technologies that come into play thanks to the new applications that we have on board our cars. And as Cinzia said, the focus will be on time-sensitive networking standards that are my favorite topic nowadays. And I will briefly introduce to you some of the main standards that are interesting for automotive usage. And then I will conclude giving some hint on how those standards of the TSN family can really be helpful for automated driving. So this is a brief overview of what I did so far in my life. Cinzia already mentioned some experience, some working experience I had. And I also sit in some standardization bodies for industrial networks. I'm in charge of several projects for my university and also research contract with companies working in the field of time and safety critical applications. So I have a grant given by Rete Ferroviaria Italiana, which is the main Italian railway company. I have solid collaborations with ST Microelectronics, and with in the past I collaborated with Magneti Marelli for several years on automated driving and support for this on the cars. So, okay, before starting with the technical part, I want to give some nice view of my career path. It could be useful for all of those can understand since the very beginning how difficult could be the life of a woman in engineering, or a woman who wants to be an engineer. So I was born in Syracuse in Sicily. At the age of 80, Sicily is here, is the small island just in the bottom of Italy. And at the age of 18, I left my hometown and went to study electronic engineering at the University of Catania. At that time, we were in the 80s, the typical objection of people was, why does a woman choose electronic engineering? Are you sure that you can make it? And well, now I can say, yes, I made it. After my PhD, I was invited to be visiting researcher at Seoul National University, South Korea. Many people were objecting, is it really worth going so far for a woman? I didn't care, I went there, and now I can say it was very good for my career as scientific development. Later on in 2014, I was guest professor at Mälardalen University in Sweden for 6 months. The typical objection at that point was, what about your family? We managed it, and this was also very good for me and for all of us, actually. And nowadays, still, my trolley is always ready for the next trip. The typical objection is, you are always far from home, or not always, often far from home. But I say, it's part of my work. So for all of us who are still in some of these initial part of their career, I wanted to give an encouragement. Go, do what you think is good for you, because you deserve this. Yes. And what about my work-life balance? In some sense, I can say I manage. So I have a nice family. This is my husband. This is my son. And this is my dog. This is my cat. These are a small picture instead of a real picture of my parents. And this is me when I have some time for sailing. Of course, I'm very far from being perfect. I'm not even striving for perfection. I know that there's always room for improvement, but I like it like this. My engagement with IEES, because I'm with IEEE and IEES since 22 years now. Well, it has been a very nice journey. I had several roles in IEES. I started as a member at large, and then I became the chair of the technical committee on factory automation, maybe the first chair in this committee, the first woman chairing this committee. And I was also re-elected, so I covered this role for two terms. Then I was again member at large. I became in 2017 the IEES representative in Women in Engineering. And since 2020, I am the IEES secretary, and as such, I chair the Constitution and Bylaws Committee. Since 2017, I have established this Women in IEES initiative that is a team of people that together cooperate to foster the women involvement in the society. We wanted to encourage young girls to take a career in STEM and of course in engineering if they are interested in engineering, and we organize events for networking, technical workshop with some mingle time to make people get together and exchange ideas, comments, experience. And I also try to reach the youngest, for instance, participating to the summer school that are relevant to the society. And our Women in IS workshops are not for women only. As you can see, we are very inclusive. For us, diversity is a value. And every time from Beijing to Washington to Vancouver to Melbourne, you know, we were organizing these events all over the world. We have always a nice number of attendees and a lot of interesting and fruitful discussion. This is a snapshot of my the core members of my group. He's Gaetano, he's Luca, and we are a nice team, and we try to make people happy of doing some nice and interesting project in collaboration with industry. So for instance, those are the finalists of a project that was about programming some small autonomous cars to reach a target while avoiding obstacles. So these are the three groups that took the first, second, third position in the competition. And the equipment was kindly provided by ST Microelectronics. So there are some people from the Automotive discrete group from ST in the Catania site that came and had interaction with my students. That was very nice. Okay, so this was just about me. Let's move to the main topic of this seminar. Speaking about cars, the number of electronic components in cars is steadily growing. We know at the very beginning, only spare components were inserted when needed, but then these components were consolidated in electronic control units. And then these electronic control units had to be interconnected in such a way to implement distributed functions. At the beginning, these electronic control units were not so many, so peer-to-peer connection were feasible, but when the number of ECUs increased, the number of links exploded. So the network were too much complex, the wiring harness was unfeasible for reason of weight and therefore higher fuel consumption and also high cost. And so for this reason, networks were introduced to interconnect the different ECUs. And nowadays we have more than 70 ECUs in cars. In some cases, we approach 100, in some cases even more. So this graph shows the share of electronics in terms of, the share of the total cost due to electronics in cars. And as you can see, this is steadily growing, okay? And the more the functions we introduce in cars, the higher is the impact of the electronics on the overall cost. Okay, in fact, now we are going towards cars that become computers on wheels, but I will discuss this shortly now. So while in the past, the primary function of the car was to move people efficiently, now, thanks to the availability of reliable hardware technologies and software components, we have a novel function that are for diverse usage. because some functions are for improving safety and comfort, but others are for diagnostics, infotainment, advanced driver assistance systems, very often with the use of cameras also. And so what is going on nowadays? It's that a new paradigm is being used in cars. We have this term, software-defined cars, which means that new services will become available simply with software updates. So this is really a major shift. And in this sense, we can say that the car has developed from a purely physical system based on mechanics to a cyber-physical system, in which we have electronic components with processing capabilities that communicate and cooperate to implement control laws and to achieve high performance and safety. The number of lines of code in a car nowadays is astonishing. Now we have more or less the same amount of line of code of an Airbus, with the difference that, of course, the cost of an airplane can be high because, of course, you don't buy an airplane for your family. But the more costly becomes the electronic part because of the software, the more challenging is the life of car makers, because people are not so keen of paying a lot of money just for some software function. Not all the people can afford this. So for the mass market, there should be a balance between the function that you offer and the cost. So what I learned in so many years of collaboration with industry, especially in the automotive sector, is the cheaper, the better. So it's a trade-off between what you want to get and how much you want to pay for this. So communication networks do have a role in this. They are crucial because all these components, all these ECUs, all the sensors, and we have a huge number of sensors of different types. We have a radar, we have ultrasonic, we have cameras, we have LiDAR. So those components need to be connected to the processing units, and they have also to be interconnected with each other to perform distributed function. So communication is of utmost importance. But what about the communication requirement? Well, we have a number of them, but to what extent one requirement dominates on the other really depends on the specific application domain. So for the time being, we just have a look on these requirements. Predictability, what does it mean? Well, most of the communication in car networks are real-time communication. This means that the correctness of the communication really depends on the timeliness. A message that is delivered too late is unuseful or even detrimental for the system it refers to. So predictable delivery time for message is a very important requirement for several networks that you find nowadays in car. Another important dimension is reliability and fault tolerance. It's important that even in the case of a fault, the car is a very complex system, even in terms of electromagnetic compatibility. So there are a lot of potential interferers. Also, the temperature range is quite challenging. So it may happen that some message is lost. And the retransmission cannot be the only way to solve this issue, because as I say, the message have timing constraint. They have a deadline within which they have to be received. So sometimes if you retransmit, you will miss the deadline and you will deliver a not valid, temporally valid message. So we need to implement some kind of redundancy, duplicate the messages in such a way that if one copy is lost, there is another one that has a chance to be received correctly. Bandwidth is also another important requirement, because some flows, for instance, those from cameras are really significant in terms of bandwidth requirement. But this really depends on the application, because some simple control loop do not need so much bandwidth. Low cost is imperative, as I said. Security is also imperative. Tampering a network car can be really a danger for the safety of the people inside the car and the people in the surroundings. And also energy efficiency is important, and so most of the network protocols are able to implement power saving functions, like for instance, sleep and wake up mode. So as I said, to what extent one aspect dominates the other ones very much depend on the specific application or functional domain. So these are the typical the traditional functional domain we have in the car: powertrain, chassis, X-by-wire, body and comfort, multimedia infotainment, advanced driver assistance. Powertrain is relevant to the control engine and transmission, chassis to the control of vehicle stability and dynamics, for instance, steering, braking, and so on. Body and comfort is relevant to the control of doors, windows, roof, seats, air conditioning, and so on. These are the traditional domains. In the first two, we have for sure real-time communication, both for powertrain and chassis. Moreover, in chassis, we also have some need for fault tolerance. And differently, body and comfort does not have anything time critical or safety critical. So here a cheaper and effective network can be used. Novel domains are multimedia infotainment. So, you know, when we stream audio, video, or when we use the navigation information service and so on, and also HMI. We also have a camera-based advanced driver assistance system, like lane departure warning, traffic sign recognition, and so on. And then automated driving from level 1 to level 5. These new domains require both real-time guarantees, and in some cases, like in the last two, they need fault tolerance and a lot of bandwidth, okay? Because the flows that are dealt with by these systems need more bandwidth, are significant flows. I will not spend so much time on current in-car networks, but we have a lot of them. So the champion in the body and comfort functional domain is the LIN bus, local interconnect network. LIN is used, for instance, for the central locking of the doors, okay? CAN, the controller area network, that comes in different flavors. We have the traditional CAN, and then we have CAN flexible data rate, and recently CAN extra large, CAN XL, is widely used in most of the functional domain in the cars. There are different speeds for different usage, from powertrain to chassis, to infotainment and comfort. And CAN is used, for instance, as a kind of backbone for the multiple LIN networks you can find on board of a car. FlexRay is also an interesting protocol. It's very nice, but it was born at the wrong time, because it was ready when in the United States there was the crisis of the automotive industry. So when it was up and running, there was not much favor in the market because of the crisis. FlexArray was born for guaranteeing temporal behavior because it's based on time division and multiple access. It's quite efficient and also high reliability because it uses two channels. FlexArray is used by some car makers up to now. It's not sure that in the future it will be used for a long time, because it's very likely that it will be superseded by Ethernet. And almost the same consideration can hold for MOS. MOS, differently from FlexArray, is quite widely used nowadays in the cars. And it's the principal de facto technology for multimedia infotainment. But for several reasons, the high cost, the fact that it's a proprietary technologies with a single provider that ask royalties to enable the others to certify the compatibility of the product. I read in different sources that it could be that most in the future, the long term, will be also replaced by Ethernet. So this was just a table I prepared to compare the different current network technology we have on board of a car. We can notice that there is a different range, of bandwidth. For instance, for body and comfort, the 20 kilobit per second of LIN are more than enough. CAN comes in the different flavors. The traditional CAN is up to 1 megabit per second, but mostly it's about 500 kilobit per second, the high-speed CAN on board of car. But in the meantime, we also have the need to support higher bit rate and longer payload. And for this reason, CAN flexible data rate was built, and it's up and running. The typical bit rate used nowadays in cars is 2 megabit per second, but the 5 megabit per second automotive grade is also available as a technology. And FlexArray, as I mentioned, offers high bandwidth. It's 10 megabit per second per channel. It implements 2 channels. So if both channels are used to convey different information, so if you don't use the second channel as for redundancy, for spatial redundancy, then FlexArray can offer 20 megabit per second and deterministic communication. So FlexArray is very useful for safety critical application in chassis and X-by-wire. MOS comes into 3 different flavors, 25, 50, and 150 megabit per second, but differently from the other technologies I mentioned, has a high cost, mainly due to the technology, and it's not suitable for safety critical application because it does not implement redundancy mechanism. And as I said, there is just one technology provider, but so far is the undisputed leader in the multimedia infotainment. But after this very fast overview, what is the takeaway lesson? Well, on board of a car, we have too many network technologies. So if you look at this scheme, which is taken from a car maker, every different colors corresponds to a different network. So you can see we have different network technologies. And when the inter-domain communication is needed because there is some function that spans across different domains. Well, at that point, gateways are needed. The gateways are there to implement a kind of protocol translation. But in the case of automotive, these are complex gateways because they need to know the application to make the proper mapping of a signal from FlexRay, for instance, to a MOST message. And this means that every time you change the application, you also need to update the gateway. So all of this is to make you aware of the real need for a common network technology. Because the less the number of different protocols, different frame format, and so on, the better. So we need to reduce the complexity, trying to have one technology or reduce the number of technologies. And there are several reasons for that. Also, diagnostics is an area in which we need high bandwidth because of the flashing time, that is the time at the repair shop or on the production line, that is needed to reprogramming the ECUs. Well, it's money. Time is money at that point. So we need to do this flashing as quick as possible. And if you use CAN, you can take, it can take 10 hours for transferring 81 megabit of updates. If you use Ethernet, you will take 20 minutes for 1 gigabyte. Also, it's important to have a network that is able to be open to the IP, so the TCP IP stack for communication with the external world. So where we are now, so we are in the 2020s. So we have these many technologies, but what will be the future? Well, I can tell you that the future will see, let's say, for sure, 3 main players. Lean, because it's the right solution for the right functional domain. And then we will have CAN protocols in the 3 different flavors, including CAN XL and Ethernet, okay? There will be MOS and FlexRay for some years still, but the tendency, what I heard from the car makers, what I heard from people working in the business is that the longest perspective is for Ethernet and CAN. But when I speak about Ethernet, I have to make some, I want to go a little bit faster. I want to be clear. What is Ethernet? We all know that Ethernet is the interconnection protocol standardized by the IEEE 802.3. And over the years, automotive grade Ethernet standards have appeared. So the first one appeared in 2015, automotive grade 100 megabit per second on a shielded twisted pair. And then we had the 1 gigabit per second, more recently 10 megabit per second, known as 10 base T1S, and the 2.5, 5, and 10 gigabit per second, standardized in 2020, and also known as a multi-gig automotive electrical Ethernet 5. And there is a work in progress within the IEEE on higher bandwidth, 25, 50, and 100 gigabit per second, okay? This is just the physical layer, but we also need something on top of this. So we need also policies at the MAC layer to implement on Ethernet communication that is real-time, predictable, and reliable. We need a lot of services to use Ethernet as the backbone for the future cars. To make it more clear, I wanted to introduce to you something about the next generation architecture of cars. So I told you that currently we have this domain-based architecture, but there is a migration ongoing to zonal architecture. In zonal architecture, Ethernet links will be used to support autonomous operation that generate data rates greater than 10 gigabit in the automotive environment. So the tendency for the future is to shift from a logical distribution of the functionalities to a physical distribution. This is a zonal architecture in which several zonal gateway controllers handle the communication with sensor and actuators on a portion of the car. And so they need to combine the network protocol typical for these devices. But this zonal controller have to be interconnected between them and with the central computer. This central computer will be performing the most complex processing. Okay, so in this framework, we need a network that has to be automotive grade, that has to be a converged network in the sense that it has to be able to support diverse flows. They can be best effort flows, they can be real-time flows, they can be flows that require determinism. Deterministic communication is a little bit more than real-time, because in real-time communication you are satisfied if you have guarantees on the maximum delivery time. When I speak about deterministic communication, I'm saying something else. I'm saying that you need that a message will be delivered at a precise time, or that need to be transmitted at precise time. So determinism is much more difficult to achieve than real-time guarantees and bounded latency. So how can it be that Ethernet became able to support real-time constraints and deterministic communication? This occurred in two steps. First, with audio-video bridging that brought Ethernet into the real-time domain, and then with TSN extension that increased, building upon something that was already realized by audio-video bridging, and some functionalities to have deterministic and reliable communication. So when we speak about Ethernet, we have to recall that we are mentioning Ethernet switches. Switches that in the IEEE terminology are called the bridge. What are them? They are the multi-port interconnection devices that enable communication. They are multi-port interconnection devices that enable communication among multiple networking devices. Switches work at the data link layer. They regenerate frames, but instead of limiting to this, like the repeaters, they are smarter. So they apply filtering and forwarding functionalities. They are able to learn and build a table. In this way, they forward the data only to the device or to the devices that need to receive it, instead of simply broadcasting the same data out of each of their ports. But is an Ethernet switch able to provide real-time guarantees? Not at all, because there is no bandwidth reservation, because the queues that are bound to each switch port are handled in first in, first out way. And moreover, as there is no bandwidth reservation in plain switches, there could be some packet loss due to the overflow of these queues. So even though we could connect to each port of a switch, a single device, even though we could have communication without collisions in this case, still we cannot provide real-time guarantees. Even the IEEE 802.1q standard that defines the procedure to be used by switch in handling Ethernet frames. This standard introduces the VLAN tag, and this can be used also to implement some kind of prioritization scheme, that can be used for quality of service. This simply means that if we have flows belonging to different priority queues, they will get a different service, but there is no way to provide any kind of guarantees. So what audio-video bridging does is to provide protocols to manage the network time, so that a common network time exists in the network. And so synchronized operation is possible. Also, it implements priority levels in such a way that real-time flows and non-real-time flows can get a different service, and bandwidth reservation. I will not go deep into the details of audio-video bridging, but I want just to give you the basics. So the timing and synchronization for time-sensitive application is one of the three main standards of this protocol family. This provides precise time synchronization of the network nodes to reference time with an accuracy better than 1 microsecond. It's very important because all the other standards build on top of the common time notion that is realized by this standard. And the other two are used to provide real-time guarantees, that is bounded latency to real-time flows. It's a contract. These flows want to have real-time guarantees over a best effort network, because Ethernet is a best effort network. So they make a contract with the network. According to those two protocols, there is a reservation of bandwidth for the real-time classes. There are two real-time classes, class A and class B. These real-time classes subscribe this contract in the sense that they will be constrained to send a maximum amount of frames in a given time interval, and also the maximum size of the frame is set according to the rules of this protocol. In order to enforce this behavior, this standard implements a credit-based shaping algorithm that enforces with a mechanism that is long to explain, but works quite well. It shapes traffic bars in such a way that these real-time flows will behave, will respect the contract with the network. And the result is that as they behave and respect the terms of the contract, they get the real-time guarantees. Class A, in fact, every flow in Class A is guaranteed a maximum latency of 2 milliseconds over 7 hops. Class B has a less tight contract, but also less strict guarantees. So there is a bounded latency over 7 hops, but it's within 50 milliseconds. So audio-video bridging has moved the Ethernet into the real-time applications domain. So this is the first step. But then we need more, because if we want to support automated driving, we need much more than bounded latency. And this is the reason why just after the audio-video bridging project was closed, and another one started, time-sensitive networking. This working group is about developing mechanisms to provide deterministic services on Ethernet, and guaranteed packet transport with bounded latency, low packet delay, and low packet delay variation, which means low jitter and low packet loss. TSN is not a single standard, it's a flexible toolkit. Depending on what you want to achieve for your application, you pick the standard you want, and you can, pile them and combine them to get to the point, to get to the result you need. So there are standards for improving the reliability, standards for resource management, standards for timing and synchronization. And here we have the one from audio-video bridging, but also a newest version that was published in 2020, which make the timing and synchronization mechanism more reliable because it introduces redundancy and multiple synchronization paths. So it makes the synchronization more robust in case of failure of a node or an additional or removal of some node. And last but not least, we have a bunch of standards to achieve bounded low latency. So I will go through them. This is a nice table which I mention all the principal TSN standards, and especially those who are relevant to automotive. There is also a ongoing project, the time-sensitive networking profile for automotive vehicle Ethernet communication, that is in progress. So I wanted to go through the bounded low latency standards. So TSN offers two mechanisms that can also be used in combination to improve the communication behavior, to give deterministic communication. So one of these is the 802.1 QBV, enhancement for scheduled traffic. Now this standard that was born as an amendment of the 802.1Q now has been enrolled in the 2018 version of the 802.1Q standard, and the same holds for this one, the QBU. So the QBV is a standard that introduces support for schedule-driven transmission over Ethernet. How does it work? So it defines policies for bridge, that is switches and stations, to schedule frame transmission based on the timing provided by the AES standard, okay? And this is a very significant step forward, because thanks to this mechanism, we can have deterministic communication. The other one I want to mention is the frame preemption. This is really interesting too, because you know what this standard means. It means that there is an ongoing transmission of a long best effort frame, and at some point, time critical frames is ready for transmission. This standard allows preemption, but is a preemption that is not destructive. So this standard that works in combination with the 802.3 BR, interspersing express traffic, enable ongoing best effort frame to be suspended. So the transmission is suspended. We can transmit one or more time critical frames, and then we can resume the transmission of the frame that was preempted. And we don't lose bandwidth. The frame is not damaged. The frame is simply split into fragments. Each fragment is terminated with a MCRC, as a kind of fragment cyclic redundancy check that allows the destination node to check that the fragment received so far is correct. And when the time critical frames have been transmitted, then the transmission of the preempted frame can be resumed from the very point at which it was suspended. Okay, so this is very interesting. We have to say that frame preemption is valuable, especially if we run at 100 megabits per second, because in that case, we can significantly reduce the latency for the frames. If we go at higher speeds from 1 gigabit on, then the benefits of preemption are reduced, but still it's very interesting. And the two standards can be combined. This also brings some benefit. Another standard I wanted to mention is the 802.1 CB. It's called frame replication and elimination for reliability. These standards provide the following functionality. So identification of the frame and replication for redundant transmissions, identification of duplicate frames, and elimination of the duplicates. So what is the spirit of this standard? It allows for frame duplication and transmission over disjoint paths and elimination at the mark layer. So basically, this means that if we have a source node, a destination node, and a number of switches between them, if the source node is not able to do it itself, is not able to implement this standard, then the first switch that is directly connected to the source node can duplicate the frame and send the two replicas over to different paths. The two replicas will go independently. The last switch, that is the one that is directly connected to the destination node, will let the first replica pass, and when the second arrives, it will be able to identify that it's a replica of something that has been already delivered, and then it will discard the replica. This is very important because, as I told you at the beginning, in real-time networks, retransmission sometimes cannot be used because the time taken for waiting for the ARC doesn't arrive, and then you retransmit, can be too long, and then we could miss the deadline. So it's much better to have two messages, two frames that go in parallel, take the first one and discard the others. Also, there is another interesting standard, the QCI, that is able to check if every flow is sending the frame at the rate that has been contracted, let's say, with the network. This standard is able to perform frame counting, filtering, policing, and therefore can be also used for security reasons. Because, for instance, if some flow is misbehaving, this means that there is something wrong. It could be an attack, it could be some bug, but in any case, there is some kind of error confinement. So these, the frame that are generated at the wrong time are simply blocked. So they cannot go through the network. So summarizing, why I like TSN, why I think that TSN is very important and very useful for cars, because TSN standard can provide all of these features: bounded low latency, very low jitter, reliable time synchronization, ultra reliability for data traffic, resource management, convergence, so one network for different kind of flows that coexist on the same network, interoperability, because TSN are IEEE standards, so they are open standard, they are, I mean, IEEE is always a guarantee in this case, and also provide the right framework for implementing security. So TSN is a very suitable option for both Industry 4.0 and for automotive networks. And TSN can offer good support for automated driving, because that automated driving application needed to fulfill the temporal constraints, time synchronization, redundancy, and error detection and mitigation. So, well, for instance, the announcement for scheduled traffic can be used for providing deterministic behavior, low latency, for steering, braking, closed loop control, inter-processor communication. It also can accommodate quite well highly regular periodic traffic. But we can also have a burst traffic, and then at this point preemption can help. And also the credit-based shaper or audio-video bridge is able to deal with burst traffic. So this is the support for temporal constraints. The time synchronization requirement can be fulfilled thanks to both the original IEEE standard from 2011, and if we also have some constraint on fault tolerance, so for instance, in the highest level of automated driving, full automated or driverless, we need redundancy to allow the system to remain operational and achieve the minimal risk condition, even in case of failure of a link of the Grandmaster. So in that case, the 2020 version, the IEEE, with the support for multiple synchronized Grandmaster and multiple synchronization path, is able to match this requirement. As I said, autonomous driving systems have not only requirements in terms of delay, but also in terms of reliability, in the sense that frames should not be lost. We cannot go through the retransmission, and then the support offered by the frame replication elimination for reliability standard perfectly matches this kind of constraint, thanks to the duplication, the disjoint path of transmission of the replicas, and then the elimination of the MAC layer. And finally, as I said, this standard QCI is able to support metering and monitoring error detection, so it can be used for prompt detection of errors due to random hardware fault or cybersecurity attack. I think that I will skip those slides, and so I finish here, and sorry if I was too long, and I would be happy to take your comments and your questions.
Thank you. Thank you very much, Lucia, for this fascinating presentation. And I will pass over to Bożena, who will deal with the question and answer sessions. So please, everybody, post your questions on the chat if you have. And waiting for the chat questions, so maybe, Bożena, I could ask a question myself.
Sure, please.
Right, so it was very interesting because, of course, security, and in particular with the really last part of your presentations, when you had really autonomous driving, were taken into account. But there are probably currently two main issues that I see that could be critical, in fact, for all the software which is related to automotive. And the first is hacking. You mentioned that briefly at the beginning, so it's part of the security. And the second is the chip crisis, so the electronics chip crisis that we're really dealing. So we don't really know how this is going to develop, but do you think we will get to a point where it will be possible just to completely suppress, so have a moment in which we will completely disconnect all the electronics and all the protocols that we have in our cars and go back to the cars that we had 20 years ago, which were completely mechanical without any electronics? Do you think it will be possible to have a switch that would do that?
Well, I don't know. I still belong to the maybe small, I don't know, group of people who are not so fascinated by too many functions, but for just the most important ones. So I don't think that we really need driverless behavior nowadays. I always think that the highest level autonomous driving, level 5, should be tested in my hometown. If it survives, maybe it's a real thing. I think that the migration to the zonal architecture can be a way to deal with the chip crisis because of hardware consolidation. So instead of having a plethora of ECUs that contains a processing element spread over the cars, each one devoted to a specific function, maybe with hardware and software consolidation in this high performance computer on board of the car, maybe can reduce the number of silicon chips that are needed. And moreover, the more you move to the software, maybe relieves from extra cost, because instead of changing the hardware, you just need to refresh, to update the software. So if we will be able to come back, not really to the oldest car, but for a while, could be that some futuristic vision should wait and face the dramatic times we are living now.
I didn't want really to be so drastic, either one or the other. What I thought was a system that deactivated in case of need. So if something goes wrong, and for various reasons, which is nothing to do with redundancy, but the fact that maybe some hacking or even other reasons, and the car would not work at all. So having a mechanism that would deactivate the intelligence.
Sure, I think so, yes. I think so. I think it's important, and in the past there are several certified examples of successful attacks. For instance, on the CAN bus, there is a lot on. So yeah, I think that it's important to be able to revert and give the control to the driver, if there is a driver. So for this reason, I said driverless is beautiful, but maybe not in the short term.
Short term. Thank you, Lucia. Thank you very much.
Thanks. I believe that I don't have the best connection, but I will try. I would like very much to say thank you, and you can see in chat people say thank you to you for this great presentation, very important topic. So to finish that session, I would like to ask you if you would say in one sentence, if you would like to stand on the top of that, whatever I can see behind you, and say to students, to young next generation, join me and do that, how you would say, what you would say to attract younger generation and students to this important area of research? What you would say?
Well, I would say, if you like it, do it. Be selfish, be brave, and don't listen to pessimistic people because they are simply envious, you know, or so narrow-minded that they don't deserve your attention. So if you like it, because I always say, if I were not so passionate about technology,
Yeah.
I could never stand the difficulties of studying engineering. It's not a cup of tea. So, but if you like it, do it. And be selfish. So if you wanted to go abroad for a working experience, simply go. Don't wait for people saying, okay, you can do it. You don't need their permission. If you want to do something, do it.
I like that. I like that tremendously.
Because sometimes I didn't take some successful path because I was waiting for the approval. People will not approve something that is against their interest. So if you want something, take it. I am not the one who took everything, no, but just because I'm now old enough, I encourage girls. I encourage everyone. So if you really like it, take it. Take the path. Engineering is not easy, but if you like it, it's fantastic.
I like very much your advice. I agree fully. Just go with your love, go with your passion, and this would work no matter what. I cannot stop asking you for personal question. You show us at the beginning your family. So you have two men in your family. What do two men do? Can I ask this question? Particularly what your son is doing?
So my son is attending the second class of the high school. And I'm pretty sure he will not take engineering because he's the son of two engineers.
This is not true because look, I have daughter of two scientists, engineers, and mathematicians, and she went for mathematics and engineering. So she combined those, and she does something totally different, neuroscience, and so on. So I don't agree with you that two engineers discourage your son from engineering. This I don't accept.
I'm not, you are right. I'm not saying that we discourage. He is an autonomous person. So I think he wants to do something else, and he's passionate about history. So he's very keen on learning history, and I will not say anything. He will do whatever he wants.
Exactly. And this agrees, can you see, and this is a follow-up of what you said to students, in general. Follow your passion, follow your love, and this will always work. Yeah, I agree. So it's perfect time to close. Cynthia, as always, you will close. But thank you once again. Thank you very much for being with us and sharing with us this really important, and I admire your knowledge of technology. Thank you.
Thank you very much. So thank you, Bozena. We are always doing that together. I would not really have been able to do all that without you. So Lucia, thank you very much. I hope we will keep in touch because what you're doing, and in particular your passion, is so inspiring that I think we will be really more of you and more of that. And thank you also to all the attendees. This is, of course, under the umbrella of the 25th anniversary of Women in Engineering. So there will be more presentation until the end of the year and even further maybe. So please keep tuned. Thank you also to all the people in the team of Ramalata Marimutu, who has been really following us from the start with the promotion, and the team within the IEEE Women in Engineering office, who is always extraordinarily with us and helping us with all the technical aspects. So thank you again. Thank you, Lucia. Thank you, everyone.
Thank you to all of you. Thank you for inviting me. Thank you for organizing
so
this.
Much. Congratulations. Thank you very much.
Bye-bye.
Bye.
Again.
Bye. Bye.
Bye.
Bye.
Bye-bye.
Bye.